Example 7.4. What is the wavelength of a photon of light in nanometers emitted during a transition from energy level n equals to 5 state to the energy level n equals to 2 state in the hydrogen atom? So we have to understand what's happening here. Assume the y-axis is energy. This is energy level 1, probably energy level 2, n equals to 3. They usually come close and close when they go up there. So an electron right now is on energy level 5 and is dropping all the way to energy level 2. And as it does so, he is going to emit a photon or a light of a given energy. And that light of given energy is going to have a given wavelength. And that wavelength has to be reported in nanometers, and that's what we need. Remember that energy is Planck's constant times frequency, but frequency is speed of light over wavelength. So the same energy is Planck's constant times speed of light over wavelength. So yeah, energy is related to wavelength. So if we can find delta E in the red, as the electron drops from n equals to 5 to n equals to 2, there's going to be a change in energy delta E. So we need to find that change in energy delta E as we move from n equals to 5 to n equals to 2. So I know that delta E is equals to Rydberg constant times the difference of inverse of n squared initial state or energy level minus the inverse of n squared final energy level. So this is the formula. And so that's gonna be our step number 1 to find delta E. So once we find delta E, we should be able to find the desired wavelength. And the desired wavelength is gonna most likely be in meters. We'll convert it to nanometers. That is our strategy. So my Rydberg constant is 2.18 times 10 to the power negative 18 joules. And then my initial energy level is 5, so I'll say 5 squared. That's where the electron starts, and then it drops to n equals to 2, so 2 squared. So I'm just plugging in the value of n's, n initial, n final. I here stands for initial, f here stands for final, and I see I'm given nf and I. Okay, so all that is left is for me to do the math. I'll firstly do what is in the parentheses. This is where now your calculator skills will help you. So doing what is in here first, this is what we're going to get. So 1 divided by 5 squared minus parentheses 1 divided by 2 squared. Okay, it's giving me negative 0.21. So this one right here is gonna be negative 0.21. Then I take that number and multiply by the Rydberg constant, 2.18 exponent negative 18. So I'm getting this very small number with a negative. So let's see how many decimal places to move to after 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So my delta E here is gonna be negative 4.578 times 10 to the power negative 19 joules. It's negative here because energy is lost. When energy is lost, you kind of say the reaction is exothermic, so we put a negative, okay? But the key information is the change in energy value, this 4.578 times 10 to the power negative 19. The negative here just means that energy is lost, implying emission of a photon. Now, to three significant figures, it will be negative 4.58 times 10 to the power negative 19 joules. Keep an eye on that. Now we are done with the first part, which was determination of change in energy. So remember, by picture, we are moving from n equals to 5 level all the way down to n equals to 2 level. The difference in energy is what we are calling delta E, and a photon is emitted. Photon is lost, energy is lost, that's why we have a negative. Now, the question does not want the change in energy. The question wants the wavelength, okay? Remember, energy equals to Planck's constant times frequency, or Planck's constant times speed of light over wavelength, because our frequency should be c over wavelength. Okay, so we need to find this wavelength in the formula of energy. So we're going to switch gears here and say, okay, so let's draw a line. So we are going to say that speed of light equals to wavelength times frequency. We know that. Therefore, from here, if we divide both sides by wavelength, we'll find that frequency is going to be equal to speed of light over wavelength. However, we also know that energy equals to Planck's constant times frequency, but frequency is the same as speed of light over wavelength, so energy is going to be equal to Planck's constant times speed of light over wavelength. Okay, our interest is the wavelength. Our interest is the wavelength. So we are going to multiply both sides by wavelength. Okay, let's solve for wavelength. So we're going to multiply both sides of this equation by wavelength. So energy times wavelength must be equal to Planck's constant times speed of light over wavelength, which is going to be also multiplied by our wavelength. Now doing so, you will see that the wavelength and wavelength will cancel, and this side you will have energy. We could now say delta E times wavelength equals to Planck's constant times c. Now our interest is the wavelength, right? So we'll divide both sides by delta E, divide both sides by delta E. What equation do we end up with? We end up with the equation that tells us that our wavelength will be equal to Planck's constant times c over delta E. Why? The reason is delta E will cancel on the left. This is very important. That is what's going to help us to solve for wavelength, but the wavelength solved for is going to be in meters. So let's do that. We are on this step in our plan. So we initially calculated delta E, done. Now we need to find wavelength, and it's going to be in meters. So to do so, we'll write our formula. Wavelength equals to Planck's constant times speed of light over divided by delta E. We know Planck's constant to be 6.626 times 10 to the power negative 34 joules seconds. That's usually provided in the test. And speed of light is a constant too. Is 3.00 times 10 to the power 8 meters per second. We know that. And we are dividing this through by delta E, which is negative 4.58. Now, wavelength cannot be negative. This wavelength cannot be negative. It has to be a positive number. So we are going just to use the positive value of the energy change. Okay, so we'll use the positive value of the delta E. We know the answer was negative, but that negative that just tells us that energy was lost. To find our wavelength, ignore the positive. Okay, so we'll take positive 4.58 times 10 to the power negative 19, because wavelength can never be negative. If you put negative here, our wavelength will end up being negative. We don't want that. So what is left now is to punch in the numbers. But before we do that, the SI unit of joules and joules will cancel, seconds and second will cancel. See, we are left with meters. Our wavelength will have some answer here in meters. It's a length, so meters. It's a length, so we have to give it in meters. Let's do the math. So we're going to take our Planck's constant 6.626, and then we will do exponent of negative 34, multiply it by 3 exponent 8, and then divide it by 4.58 exponent negative 19. So we are getting 4.34 exponent negative 7. So 4.3436 times 10 to the power negative 7 meters. However, we have to convert it to nanometers. Read the question. What is the wavelength of a photon in nanometers emitted during a transition of an electron from n equals to 5 to n equals to 2 in hydrogen atom? So I know that 1 times 10 to the power negative 9 meters is actually equivalent to 1 nanometer. So I'll take my 4.34 times 10 to the power minus 7 meters and multiply by my conversion factor. I want my nanometers to be numerator because that's where I'm going. So 1 nanometer is equivalent to 1 times 10 to the power minus 9 meters. Doing so, m and m will cancel. We are left with our answer in nanometers. And this answer is going to be 434 nanometers for our wavelength. So our wavelength is going to be 434 nanometers of a photon transitioning from n equals to 5 to n equals to 2. Okay, that will be the answer. The wavelength will be 434. I know I don't need a calculator here, because if you say 10 minus 7 divided by 10 minus 5 is like subtracting. When you're dividing powers, it's like you're subtracting them. So it's just like saying 10 minus 7 minus 9. That is just 10 to the power 2. So if you take 434 and multiply by 10 to the power 2, which is 100, you're going 2 steps, 1, 2. I don't need a calculator. The answer will be 434. So that's the answer.